So we have this a pipe, and there's a fluid going through, and for this one we're going to use our coordinate is based on a radius, because it's cylindrical coordinates. So when we're solving this question with Naveir Stokes approach, first we have to determine whether it is a rectangular or cylindrical coordinates. Because we are solving a cylindrical question, we're going to use cylindrical coordinates, of course. And after that, you have to ask, so what's the direction of the fluid flow? Because I defined it to z directions, or I set this as z, and it is not going, and the fluid is not going through radial direction nor theta direction either. So of course it's going to be z direction. Okay, so then we know what kind of equation to use. So this is the equations to use, and left side all goes out as usual, and for this one there's no change in velocity in radial direction. That simply doesn't make sense, because of what this means is that, for example, if you have this cylinder, so we have this long cylinder fluid going through this way, and that means the fluid velocity is changing depends on whether it's over here or here. Even though it's in the same radius direction, depends on where we are in terms of theta angle. It's speed is changing, which is not the case. So this that goes out, and Vz over change in z. So depends on whether the fluid is over here, even if it's in the same radius. So if whether it's on at the beginning or at the end, the fluid velocity is different, even though if it's in the same radius, which isn't the case because it's fully developed scale. The only thing that's changing is it probably looks something like that. So in terms of radius, it will change, but in terms of length, it won't. So that also goes out. And we are not taking pressure difference because it's a pressure-driven case. It's going to stay. And for this one, we're not really taking account for effect of gravity. So that goes out as well. So if it simplifies to these equations, and what we want to do, so I just moved this dpz0 to the left, and we're going to use this to get the velocity profile. So I'm going to move it to the left. So we'll have 1 over r vc. Okay. And then we can move the r to the left. Which will get this thing. And after that, we can take integral. If you take integral, we're going to get r squared, right? Yeah, because we're taking, yeah, okay, that works. And then we should put 2. Okay, and then we will have vz dr. After that, we can take the integral again. Oh, I forgot the C1. Okay. After that, we're gonna take, oh, I forgot the R here. There's supposed to be R. So put R, 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 and R. So what we can do, we can divide it by R to get rid of it. So it's still R, but C1 over R. Okay. Now we're gonna take, is it better this way? We'll try. So after that, we're going to, no, I think that's too much. Okay. Take integral one more time, and that will give us Vz, the velocity profile, with respect to R, And if we take integral, it's going to be r squared again, but now it's going to be 4. And then c1 over r becomes c1 ln r plus c2. So this is the basic form. Now, we need to figure out c1 and c2. One of the boundary condition is that we know, okay, so at the center, we know the velocity is going to be the highest. At the wall, velocity will be equal to 0. So let's do that. C1, okay. As you can see, this is parabolic shape. So what it means is at this point, when r is equal to 0, the change in velocity will be 0 because it's flat. So we can use this equation, this dv dr, at r equals 0 equals 0. And we put the rest of it, and it gives me c1 over 0 is 0, which indicates that c1 must be 0. Second boundary condition. At the wall, the velocity is going to be equal to 0. So Vc, when r is equal to big R, we know that the velocity is going to be 0. We plug it in. dp dz big R squared plus c1, we know this is 0, and c2, and this is going to be 0. So we know from this that c2 is going to be equal to negative 1/4 r squared. Okay. When we plug it back, we'll get the complete velocity profile, 1/4 mu dp dz r squared plus c1 is 0, so just c2, which is going to be negative 1/4 mu dp dz big R squared. And we can further simplify it. dp dz, okay, r squared minus big R squared. And that's the velocity profile. And now we want to get a pressure gradient. In other words, dp dz. And we're given a flow rate. I think we'll be able to figure out with using the flow rate. Let's go. So flow rate is really velocity average times area. But in our case, we don't know the V average, but what we know is the velocity profile. And we can use that by simply doing, if this is a cross section of the pipe, this is the center, and yes, this is poor drawing, but this is one ring, and we're going to call this dr. So area of this ring is defined as 2 pi r times dr, because if we unfold this and stretch it out, it's going to look like a wrong rectangle. And because this is at like a one specific radius, they have uniform velocity. So we can use VR, our velocity, or VZ, with respect to R. So that's our velocity profile times area, which is, as I said, 2 pi r times dr. And this only goes from 0, when r is equal to 0, to big R. Okay. the same thing. So we're gonna plug, if you put our velocity profile in here, is that okay? Mu dp dz small r squared minus big R squared times 2 pi r dr. And we can get some stuff out that are just constant. So 2, 1 over 2 pi mu dp dz. Anything else? No, I think that's it. Actually, yeah. So the rest goes like that. And in this case, we can solve this by making it into these two separate r cubed dr. Okay, now I could probably pull this to the front, but we can solve it. If you take integral, we'll get r4 r3 minus r squared 2 big R squared that okay, we'll have that, and then we can finish this integral. Same thing as that, and our fourth, so so it will look like r fourth, oh not fourth, r to the power 4 minus r to the power 4 over 2, and this will become r to the power 4 over 4 negative. Okay, and this makes sense because dp over dz is negative, so this negative sign cancels out. Because pressure, why is dp dz negative? Because pressure goes from flow from high to low, right? And z's direction is defined, positive z direction is this way. So, and flows, since flows are going from here to here, pressure will be higher over here than this side. So the pressure is getting lower as the z is going higher. So that's why dp dz is always negative. And this sign stuff goes, cancels out at the end. So 8 mu r to the 4th, no, I'm going to write that later, dp dz r to the 4th. And that is our q dot. Oops. So now that we know our q dot with dp dz term, we should be able to solve for dp dz. Because on this problem, q is already given. So let's solve for dp dz. the pressure gradient. Q Q goes up, R fourth goes down, 8 mu goes up, pi goes down. Okay, so this is what it looks like. We are given Q, we are given a big R, given the mu, we should be able to solve for pressure gradient. Now, let's solve for maximum blood velocity. We know from this profile that when R is equal to 0, so when it's at the very center, the velocity will be the highest. Since we have this velocity profile expression or equation, just by simply plugging R is equal to 0, we'll be able to solve for maximum velocity. So Vmax happens at R equals 0. So Vz, R equals 0, will give us 1 for mu dp dz and 0 minus R squared. And as I said, dp dz is negative sign, so these negative signs cancel out. And just by simply doing that, we'll be able to get the maximum velocity. From that, we can also solve wall shear stress. So shear stress is defined by mu times gamma dot, where mu is viscosity, and this is shear rate. And shear rate is defined as du over dz, or well, in our case, since this is cylindrical, we should say dv over dr. And we actually have that from our previous calculation right over here. So shear rate is equal to that. 1 over 2 mu dp dz r plus c1 over r, but since we know that c1 is 0 now, so that's what this is all equal to. And we can plug this back into theta. Wait, no, it's not theta, tau, our shear rate, no, shear stress. So shear stress is equal to mu times that. Oh, but the mu will cancel out. So we'll simply have 1 over 2 dp dz times r. Pretty simple. But this is shear stress and not wall shear stress. In order to figure out, we have to put when R is equal to R, big R, so at the wall, big R, right? And that will give us the wall shear stress. I'm just going to denote it as WSS, wall shear stress, is equal to dp dz times big R. And that is our wall shear stress expression.